calculations. Do these calculations look familiar to you? You've been forced to do some of these calculations?
Yes.
Yes, good. Okay, the Earn model is great because, when do these calculations get easy? There's only one situation you can call out when these calculations get easy.
Conjugate.
When it's called conjugate, right. So in this case, the beta distribution is conjugate to the binomial distribution. I'm not going to go through that, but essentially, with conjugate distributions, you have pseudo. You can express the prior in terms of pseudo observations. A conjugate prior is a certain number of observations, and then you say, that's actually it's a certain number of sufficient statistics of observations. In this case, the sufficient statistic is the number of zeros and the number of ones. And so you can express your prior as alpha 1 and alpha 0, which are numbers of zeros and numbers of ones. Let's just take a moment to see what different values of alpha 0 and alpha 1 mean. Now, the nice thing about this Earn model is we are not bothering with this posterior step. We're cutting the Earn model, does all the integration for you, goes straight through to the predictive step. So if you're betting against people, you're betting on tosses of biased coins or rolls of biased dice, which is maybe slightly more realistic, and you're deciding to use a conjugate prior distribution over the outcomes, you can just have an Earn, and every time you can put in some observations at the start to express your prior beliefs before you've seen anything, and then every observation you take, you just put another observation into this Earn. And then you can then predict the next observation, or rather the predicted probability is then the distribution of observations that comes out of that Earn. You can even, if you have this solitary game of pulling things out of an Earn, that's like a sort of Bayesian fantasy. You're sitting there having a Bayesian fantasy, you're saying, I'm starting off with a prior probability, and let's see what sorts of sequences of observations might I see. So, so if you take a Polylearn, you can show that it eventually goes to a limiting number fraction of zeros and ones. So the fraction of zeros and ones in the Earn eventually remains stable and tends to a value almost surely and tends to infinity. If you look at the entire sequence, it looks like a sequence of Bernoulli draws, independent draws, given that eventual value. Let's not go there. Let's just view this Earn model as a great system of making draws according to the predicted distribution. Okay? I mean, you could say, I've got a biased coin, whereas in fact you've got an Earn. So you can play the game the other way around. You say, I've got a biased coin, I'm going to sit. And every time you make a draw, you're using your Earn. That way you didn't know what the bias of your coin was to start with, but you find out actually as you do more and more draws from the Earn. It's another way of looking at it. Okay. All right. So we've got these. Let's just think what these different prior distributions mean. See what this does. This claims to be a whiteboard marker, so it's dangerous. It is. Yes. So alpha 0 and it's better than mine, alpha 1 determine the prior. And then the Earn model. If we have alpha 0 equals 1 and alpha 1 equals 1, we have a uniform prior. 1, 1. If we put alpha 0 equals, say, I don't know, 20, alpha 1 equals 20, what's that phi going to look like intuitively? It's going to be pretty peaked in the middle. Once you've started it off with 20 of each colour, it's not going to drift far away from that. We keep on pulling them out at the same rate. It's going to be peaked around the half. Okay? Now we can have a weird prior. We could have, say, alpha 0 equals 0.1, and alpha 1 equals 0.1. So we're putting a fraction of an observation into each. What does this mean? This is a different kind of prior belief. And what you actually get, one, is something like this. Okay? Because think about this. Once you draw 1, if you've drawn 1, 0, if you draw a single 0, then the next time your probability of drawing 0 is 1 plus 0.1 over 1 plus 0.2. So it's like 11/12 is your next probability of drawing 0. So what you're saying is this is a kind of prior belief. So among the prior beliefs you can specify by this method, this is the sort of range of types of prior belief you can specify. You can specify a uniform one, 1, 1, something peaked either in the middle, or you could have alpha is 0 is 50 and alpha 1 is 10. Then it's very strongly down here. You can specify kind of peaked priors, and you can also specify, slightly bizarrely, something like this. That's the range of kinds of prior belief you can specify using these figures in the air.
Excuse me, is this related to Dirichlet distributions?
Yes. The beta distribution is the Dirichlet distribution on 2 variables, on dimension 2, and this is exactly, so you can have exactly the same error arguments with Dirichlet distributions. Again, you put fractional amounts in, and all the same arguments carry through. So I always find, for a long time, I found Dirichlet distributions really hard to imagine. Actually, the Dirichlet distribution is it's the your predicted probability from it is your initial parameters plus whatever observations you have. Right. So these are the possible. These are. Okay. Right. So, but this process of urn drawing looks vaguely similar to the breeding, but as soon as we draw something from an urn and we put it back in, that's a little bit the number of balls in the urn keeps growing, whereas with breeding we're always killing one, then drawing one and putting one back in. So breeding is exactly the same idea, but with an urn with a constant number of balls in it. We're always like, it's like we've got our urn, and we sort of bend over it, and the balls all cry out an alarm and run around, but we shoot one, or throw it out into the mathematical void, where it is never imagined again, it's utter oblivion. And then we draw one, and then put another one back in. So it's kind of very similar, but staying with an urn of constant size. So, let us do that. So everyone happy with these urns at the moment? Reasonably happy with the urns. Okay? The urn model is a great way of getting the predicted distribution without ever going through the trial. for the Dirichlet and beta models. Going to keep this well. So let's return to our tiny genetic algorithm breeding model, and then we will see, I hope, connection. Let's get rid of the whole lot. All right. So I think, let me see, the best way around to do this is to say the TGA as more. Right. So with the TGA, so let's suppose we have consider. So consider TGA at the moment we have tossed out, we have killed a random individual. Okay, and we're about to breed another. Breed. Okay, this looks remarkably like, looks just like an urn with N0, did I do it wrong? N0 plus U0 zeros. Oh, how annoying. And N1 plus U1 ones. Oh. It's not quite U0. And it's N1 plus. Let's just call these alpha zeros and then 1 plus alpha 1. Let's figure out what alpha is. Now, why? What's this? Well, alpha 1 and alpha 0 related to U1 and I've done it right after all. U0. How? Sorry, I thought I'd gone wrong. I haven't. Okay. Now, according to urn, P1 equals N1 plus alpha 1 over N minus 1 killed a bull. Okay. Right, so probability of 1 is N1 plus alpha 1 over N minus 1 plus alpha. Because there are N minus 1 plus alpha bulls. Okay? But I want that to be equal. I want this to be equal to 1 minus u into so we can let's find u in terms of alpha, okay? Chance of their mutation is u. Probable mutation is u. How about that? Okay. We want to set alpha, that is, we want to convert, we can define alpha to achieve the same effect as u. So this is the subtlety of it. U equals n minus 1 plus alpha, right? The chance of mutation here. Let's figure out what u is in terms of this. I know what. You've all been copying stuff down. I'm going to make you do this. Then I'm going to do it. Let's see if we get to the same result. Come on. So what is alpha? Solve for alpha in terms of u. This is a small algebra problem for you guys. Is that okay? Try. Does that do it? Right, and if we divide up u up in ratio, so u naught is so alpha 0 equals n minus 1 into u 0 over 1 minus u and alpha 1. That will do it. So at the moment you might say, well, that's all very well, Chris. That's a ordered bubble. What you've shown is actually a certain point. If I define an earn process with these alphas, I took an earn with those alphas, and then I do the whole fantasy thing, right? And I've got to n-1 balls, then the draw of the nth ball is going to be just like breeding. The draw of the nth ball and only the nth ball is going to be just like breeding. So what? Well, the answer is actually that's enough. It's okay. Subtly, we've got it. Actually, the breeding distribution is exactly the earned distribution with n balls in it, once you've got n balls. And that's the first. Let's see why. The argument is slightly subtle and goes back to market tendency. Now let's go over here. These are the draws from the Polylearn process here. Okay. So let's look at all this. Here's your Polylearn, you're drawing out these balls. And what you notice is that if we've drawn, I don't know, 3 0, well, how many? We did 3 zeros and 2 1s. The probability of all sequences with the same with 3 zeros and 2 1s are going to be the same. Because look, you see all the denominators are alpha plus 1, alpha plus 2, alpha plus 4, and all the numerators are alpha 0 plus 1, alpha 0 plus 2, and alpha 1, alpha 1 plus 1. It doesn't matter which numerator is associated with which denominator, they all multiply out. This sort of interesting property, this property is called this property is called exchangeability. They say this sequence is exchangeable. It has the same probability no matter what order it's in. Let's where am I going to write? Yeah, I'm going to rub this one. That's what I've done. The sequence definition. Even right down up here. I always find this notation slightly weird. This is any permutation. I'm going to write this because this is how you see the definition in books. But what it means is, I think it's very concrete, with the things coming out of the urn. It's slightly bizarre. With that particular urn process, right? That particular urn process, all you need, the probability of drawing ones, so let's say, I know 5 ones and 17 zeros, is the same, however those 5 ones and 17 zeros are arranged. And when you think about it, that's truly bizarre, because every time you're drawing one, you're putting other stuff back into the urn. So the probabilities of ones and zeros are changing. I mean, isn't that strange? I mean, if you draw 5 ones, supposing you draw all 17 zeros first, then you've got 17 zeros in that urn, plus whatever you had at the beginning, and then 5 ones in a row. So the probability of drawing a 1 is much lower at that point. But it's exactly the same probability as if you started off drawing all 5 ones, and then you drew 17 zeros. I mean, it's this multiplying out thing here. This is the statement that proves it. This does not depend on the order in which zeros and ones appear. Okay? Now, this exchangeability property enables us to do something slick. I mean, exchangeability has many, is fundamental in Bayesian inference, but it's going to enable us to do something slick. So, what we established over here is on the draw of the nth ball of an urn, if we fixed alpha 0 and alpha 1 in terms of u, that single draw looks just like breeding. Okay? So we've fixed, we've kind of cheated, we've used a mathematical pun to make that draw just like breeding at that moment. That doesn't look like it's enough to imply much, but actually it does. And this is how. So, having established this, are you happy that with this weird fact that drawing these ones and zeros out of the urn doesn't matter which order they're in? And you're just convinced by the rules for multiplying out fractions. I agree, it is absolutely not terribly intuitive. I could give you another intuitive argument, but let's not. Okay. So, let's take it to here. They didn't even see the blackboard. Honestly. Came in late. Why could they tell? Right. So, making a markup chain with what is called Gibbs sampling. That's Gibbs sampling count. So I've already asked whether Gibbs sampling has come up anywhere. Has this come up in your course yet? I think it will. No?
Yes. In machine vision.
In machine vision, right? You just mean machine, right? Okay, Gibbs sampling. Okay, suppose we have n random variables. On these, okay, And let's just call these things theta 1 to theta n, like our genomes thing here. And suppose we supposing we can calculate, if you like, pi of any theta k, given all the other ones. Okay, so if we rub out one of them, we can calculate what the probability of putting a 1 or a 0 is. This is like our breeding probability calculations. This is exactly what. Okay, we will just define how to breed, but here we're going to have a probability distribution. Right? Now, so if we can do that, this is calculate. Right. Then we can define a Markov chain with states being values of transitions doing resampling let's, for the sake of it, randomly selected. It's not quite true, you have to have it randomly selected. With mine, let's have it randomly selected. Theta k. Okay, so theta k new, k, if you like, new is sampled according to a p of probably all the rest. So if you're using graphical models, for example, Gibbs sampling is this nasty method of sampling. In graphical models, if you've got graphical models with binary variables, right, you've just been using Markov random fields, you have a graphical model, you've got these things. If you can compute the probability of one node of this graphical model according to the neighbors, then you resample that. And then you do it for another one, then you do another one. And then that's how you try and get the joint distribution on your graphical model. And I'm sure if there was lecturing in the graphical model session, they will have said, Gibbs sampling usually doesn't work very well, it's very slow. But it gets there. Now the reason it gets there is what we have said, now the key observation, which I've been working up to over a long time, if theta 1, theta are distributed according to pi, okay, if they're already in this joint distribution, then resampling theta k new till the use that distribution invariant. So let's think of it as so if you're Gibbs sampling, okay, what you're doing is you're making a transition from, you're only changing one of the values of these variables. Okay? So you're progressing, there's a huge state space because there are n variables, so your state space is sort of exponential size, and you're sampling by jumping around by just changing one variable at a time. If you start in the wrong place, if you start way out at the edge, in a state you're very, very, very seldom going to visit, eventually you'll get that, and you get around the book, and it'll get all around state space, and the equilibrium distribution of that walk, you have lots and lots of little red dots that are doing that walk, will go to, it must go to an equilibrium because it's a Markov chain, and the equilibrium distribution must be pi. So when I write it up in, oh, let's see, it's orange because I haven't used it yet. Equilibrium distribution of this sampling is pi. For answer is y. Well, Gibbs sampling is a finite Markov chain, and unless something's gone horribly wrong, it's not going to be periodic, it's not going to be disconnected, so it's got to have a unique distribution, and it actually leaves distribution invariant. So if you've got loads of red dots all distributed according to pi, there's a distribution of those red dots. You're going to change some red dots around, but they're going to be invariant. The distribution is going to be invariant. So it'll get you to pi. May do it slowly, but it gets there. So, the key thing about the urn model is that its distribution was exchangeable, and so if we shoot a ball in the urn and then resample that ball from the other balls in the urn, we leave, if you like, the urn model distribution invariant. So if you have an exchangeable distributions are nice. Let me write it up explicitly. If you like theta n, or theta n given theta 1, comma. Okay, then since it's exchangeable, we can pretend when any that was the last observation. Okay? An urn is an urn is an urn. It didn't matter. The probability of an urn, particular collection of balls in the urn, is the same no matter what order they were drawn in. So if we've shown that the nth draw from the urn nth okay, we showed that. So tiny GA breeding this is moderately subtle. We've taken a genetic algorithm argument motivated by, which geneticists use, and we said, wait a moment, if we can fix things, we can take a well-known statistics distribution and we can make that genetic algorithm breeding identical to a Markov chain method of gift sampling, which leaves that statistical which will converge to that predicted distribution. So what this means, well that's rather nice. So let's conclude at this point. How much of a second break do you want, or shall I carry on? Right, I'm going to. Okay, so no. I was going to say right. Let's write this up in red because it's kind of a distinguished thing. So in the tiny GA, the probability of n0 and n1 with n0 plus n1 equals n, given a mutation rate u, equals, right, well we said drawing a sequence, right, we've got a huge little thing here. The denominators were alpha, alpha plus 1, alpha plus 2, to alpha plus n minus 1. There's n minus 1 additional balls plus alpha balls you put in at the start. That's what's on the bottom here. And then there's n0. So then you've got to have the first one is alpha 0. So you get your first 0 ball. by drawing alpha 0. Alpha 0 plus 1, that's your second, up to alpha 0 plus n0 minus 1. That's how you get your n0, so there are sort of n0 terms, times alpha 1 plus 1, alpha 1 plus n1 minus 1. So this gives you your ordered sequence, the probability of your ordered sequence of n1 1s and n0 zeros. We'd better count those ordered sequences because we're lumping them all together. So we'd better have a binomial coefficient here in, and that's going to be n, I don't know, n0, whatever. So we got it. This is quite an interesting expression, because when you think about it, if alphas, let's contemplate this expression for a bit. This is one of the more satisfying formulae you can look at. Yeah?
Sorry, before we do, the binomial coefficient, that was...
Right, okay. This is the probability of a particular sequence. This is of a particular sequence. I know 1, 1, 0, 1, 0, 0, 1 of n0 zeros and n1 ones. Okay? So we'd better count those. Those all have the same probability because we multiply to all these terms and we can rearrange the numerators in this nice way. Okay? So this is n0 terms. And this is n1 terms, okay? And you haven't got one, it's alpha 1 now, right? Okay, but this is the, but hang on a moment, but I said on the left-hand side, it's the probability of n0 and n1. So I want to collect all that together. Right? So I want to count all of those sequences of n0 and n1, so I put in the binomial coefficient for that reason there. Is that okay? And this is kind of a neat formula because what we've got, looking at it, we've got two things kind of fighting with each other which are kind of pretty evenly matched. So let's write this thing up here, equals, well, what is it? It's n factorial over n0 factorial n1 factorial, which is that, times, what is this? This alpha naught plus 1 to alpha naught plus n0 minus 1, 1 plus 1 plus n1 plus 1 over alpha we need a 1 over n in that for some reason. We're going to discover in a moment. We do need a 1 over n in that for a reason. Quite sure why. So, but n factorial, that's a bit like this. This is like a factorial thing. If alpha equals 1, okay, what does it? This becomes, Actually, if alpha equals 2. Alright? Yeah. Oh, that's alright. No, we don't need this. Sorry, there's an equal sign. That's okay, it's fine. Confused for one moment. If alpha equals 2, alpha 0 equals alpha 1 equals 1, then we're cheating. All these things become factorials. It's great. It becomes n factorial over n naught factorial and 1 factorial times alpha 0 is 1. That's just 1 here. This is just 1 plus that, so that's just n naught factorial. That's just n1 factorial. And this becomes 2 plus, this is n plus 1 factorial equals 1 over n plus 1. What does this mean? This is a key case. What does this mean? Come on. Have a break. Contemplate what this means. We said here, we've got here the probability of n naught and n1 with them assigned to n, given u here. If alpha is 0 and at particular values, what's happening? Yeah.
So which expression is that reducing to the bottom part of the whole? Is that the whole thing?
This is the whole thing. This is like a factorial. That's we're starting an alpha instead of at 1.
What does that mean?
Right? Is that okay? This is like a factorial, so it's like an alpha naught instead of 1. If we get to the point, if we choose u, choose mutation rate, so that, I know, so relatively small room, you've concentrated very hard. How long have you been listening to computer graphics before this? Only an hour? Okay, you've been listening to me for 2 hours. This is a moment to sit and take stock here. Finally, sorry, it's taken a while. We've got to something kind of reasonably nice. What we've actually done is we've totally solved the tiny genetic algorithm. And so now for a particular mutation, from this if we take a particular mutation, we choose u, so that according to the formula I had up before, alpha naught and alpha 1 are both equal to 1 and alpha is 2. Right? Alpha is this Bayesian meaningful parameter. That's our prior. Then what we've actually got here is that what this means is that with this particular value of alpha, with this value of alpha equals 2, all numbers of, or all fractions of ones in the population are equally probable. Are equally probable. So, this is when so U is usually, so n's large. use kind of roughly, so sorry, use a small number, so use roughly 2 over n. Okay. So what's happening is that, let's think about this. You've got a mutation. Supposing you've got massive numbers of mutations. Supposing every breeding is a mutation. Dreadful situation. What happens? Every breeding is a mutation. You're not inheriting anything at all. Because all your genes are just totally random. Oh, for this tiny genetic algorithm, it means all the genes are totally random. It means that basically your distribution of your numbers of zeros and ones in your population is a binomial distribution. Okay? For a u very small, the u is 2 over n. This is kind of a special value. For u something like that. The large for high mutation rates you have it like that. It's quite interesting. You have 0 to that. Absolutely equal. Or fraction of ones. Actually, this isn't quite a continuous line, it is all dots because there are n plus 1 possibilities. Okay, there are bars. That's your distribution of fractions of ones. You have any number of ones with equal probability. For a small rotation, for low mutation rates, for low mutation rates, your populations are either going to be nearly all zeros or nearly all ones, and not much in between. Okay? Right. And the mutation rate you need, the effect of the mutation rate scales with population size. So, we've had quite a long track, a slight detour through Bayesian theory. We've looked at Markov claims, and we've got to a what's going on here? If let's suppose these alphas are really big. In this case, you want to have the biggest possible ratios of each of these terms to each of those terms. If these are all 10, let's say alpha naught's 10. Then you have the great. You can sort of imagine converting corresponding terms into ratios. You get the biggest product of ratios when you have, on average, the smallest terms up here. If these alphas on the other hand are really small, okay, then you don't want to hit alpha 0. So if you can have alpha 0, alpha 0 plus 1 to alpha, if you can put all the terms into here and you remove all these terms completely, that's the highest probability you can have. But so we've got explicit, exact expressions for the probability of each number that ends under an equilibrium in this genetic algorithm. So what can we do with that? Another way of convincing you that we have actually arrived somewhere is that when you're setting up a genetic algorithm, you're facing problems. You face a problem of, okay, what mutation rate should I choose? And what population size should I choose? I don't know. Let's just think of some random figures. Let's take a population of 50, population 200. I don't know. What mutation rate should I choose? Well, if you've got a population, if you're using binary strings, and you have a population of size 200, then a mutation rate of 0.01, which is 2 over n, is critical. That's the mutation rate at which your equilibrium distribution, you can have any number of zeros with no selection. You can have any number of, the probability of any fraction of zeros or ones in the population is the same. If you say, oh, I'm impatient, I want to have a mutation rate of 0.05 when I've got a population size of 200, what's happening is you're having a strong prior bias to having, if you like, in every column of your genetic algorithm, at every lox with zeros and ones, you're going to have a mixture of zeros and ones throughout it. You'll need very powerful selection if you want it to converge to one particular value. If on the other hand you say, oh, what the hell? I'll just have a mutation of 0.001. That's a low mutation rate. So that means without selection, each, if you like, column of your genetic algorithm is going to be either nearly all zeros or nearly all ones, and very rarely something in between. And so what we've got is a relationship. We've related mutation rate and population size to, if you like, a prior distribution with a fraction of zeros. Can I write that down? Let's do that. This will give you the point of where we've got to right now. So we have related n and u to calculate, if you like, prior probability distribution of the fraction of ones in a column. I'm saying this is the prior probability distribution because we haven't put in any selection. Okay? So in this case, your breeding is like a prior distribution. Certain configurations without selection, certain configurations of zeros and ones are much more probable than others. If we have a high mutation rate, we're much more likely to have, it's far more probable to have, say roughly 50% zeros and ones in a column than to have all ones or all zeros. At this sort of critical level, it actually evens out. The binomial coefficient is exactly cancelled by this. And for low mutation rates, each column is either going to be either all zeros or all ones. So this is worth knowing. This is actually, bizarrely, already totally not in genetic algorithms books. If you read John Rowe's book on genetic algorithms, he says, oh, well, you should size it. You should have a population of about size 50, and you should have one mutation per genome per generation. In other words, he's not relating the mutation rate at all to the population size. He's relating it to the size of your genome. Ken Dion, who's quite a thoughtful guy in genetic algorithms field, again, he's aware of some of these issues. He hasn't calculated this. Geneticists calculated this for 60 years ago. It's been this. I feel this particular calculation, I think, is the most elegant of all the calculations of the distributions of frequency, gene frequency under drift you can do. I guess it was done in slightly more generality way back, well, it was certainly done in the 50s and in greatest generality by Ewens in 72. The evolutionary computation people haven't even read this. It's absolutely clear. You read their books, they don't know. They don't even know there is such a, I mean, it's really kind of remarkable. Ken Dion, in his book, occasionally asks a question like this, asks a population genetic question, then he does a simulation. That's amazing. But this particular formulation, I've set it up very carefully so that we have so that this calculation is exact and it's doing Gibbs sampling. So let's put in selection into the tiny genetic algorithm. Maybe I should do selection next week. You up for selection now? Selection next week. I embarrassed myself by snoring loud. I don't know what I did through this thing, but in many of you, this is a warm room. Perhaps we should open all the windows and freeze. I don't know. Everyone's going to wake up. People say no. Actually, we want to go to sleep. Just don't disturb me. Drones slightly. You want to go to sleep? Hey, what about me? No. I'm interested. It's all right. I'm still interested. So this is essentially a prior distribution. You imagine visualizing your genetic algorithm. Each column of it, if you're breeding it right, and there's no reason not to breed it right, none of our breeding schemes are any more plausible than this breeding scheme, is going to be a tiny genetic algorithm. So the whole pattern of zeros and ones, this gives you the prior distribution of that. And as you can see, it's a pretty damn powerful prior. And this is exactly analogous to prior distributions on biased coins, precisely the same formula distributions and everything. If you have more than one value, it's exactly the Dirichlet distribution. If you have what geneticists call the infinite alleles model, which is that every mutation gives you a brand new allele, you have an infinite number of possible alleles, so you never mutate to the same thing, which is reasonable if your locus is kind of a whole sequence, then you get a Dirichlet process. Actually, the equations for the Chinese restaurant process and the Dirichlet processes were first derived in genetics. So really, we should put them together as genetic algorithms, and why not? That's where they came from. Ewens, the geneticists were interested in it for quite another reason. They were interested in getting genetic data and figuring out in nature if there had been selection. They weren't interested in running genetic algorithms. As we saw, the last time I saw you, which was an astoundingly long time ago, so much has happened since, I don't know about you, a lot happened to me, but I seem to remember distantly showing you a paper on the evolution of the eye, where geneticists showed you a potential upgrade path. They're really not interested in algorithms. They are truly not interested in running this thing and seeing if it works. The next thing that you should be raising eyebrows at is that GA breeding is identical to Gibbs sampling, but hang on a moment. I mean, it may be an early stage of the course now, but the guy talking to you about Gibbs sampling will have said to you, yes, but Gibbs sampling takes an awfully long time to work. Whenever you can think of a better Markov chain method or a sort of a better method, use something else, because I mean, Gibbs sampling is terribly slow. Genetic algorithm breeding is Gibbs sampling. Should give one pause to think. Right. let's put in selection into this tiny genetic algorithm. What shall I rub out? Shall I rub out left or right? Sorry? Both? Was it both? Left. Okay. Both, or possibly more strategically, you should say nothing. Some of you may be getting anxious, wondering, is he going to do this every week? The answer is no. This particular talk contains quite a large fraction of everything I want you to understand. It's quite a significantly large fraction of the course. So this is a heavier than average week. There's a series of really quite subtle concepts in here. The next question you may be asking is he going to give us some notes about that? Well, the answer is yes. If one of you would like to give me what you have written down, I will convert it into retrospective, beautiful slides. Well, possibly not beautiful slides, but coherent text, checking that everything has been said in the right order and everything has been said. So if someone, preferably with neat handwriting, who has been awake throughout most of the thing, you may laugh, honestly. When I was doing maths, I realised towards the end of my first year that I hadn't been to quite a lot of well, I had been to second year lectures. I've been to quite a few of those, but hadn't been to a great many lectures, I suppose. So I did talk to a friend of mine, who was a girl, had the most beautiful handwriting, beautiful, neat, sort of copper plate handwriting. So I borrowed her notes and photocopied them. And I got a first and she got a third. We were friends again, but it took a little while. All right, so let's do this. Now, TGA, tiny genetic algorithm with selection. Again, I want to be particularly careful about putting in selection. I want to put it in exactly the right way, just as I insisted on killing before breeding instead of breeding and then killing. I'm going to put in selection very carefully so that we can directly view it as good sampling. Keep this thing here. So we have, as usual, we've got theta 1, theta 2, theta k, we're going to breed, and theta n. And our thicknesses now, we've got f of theta 1, and we now know that we've got without, in the absence of selection, we can give a probability to whatever collection of values we have here, given u. We can convert u to alpha, given n and u. We've got a. Oh, I should have said that this distribution up here is the beta binomial distribution. Sometimes it's also known as the binomial beta distribution, but hey. Right. This is here. I'm going to put that f that 0 is strictly less than f of theta is less than equal to 1. And new breeding with fitness. Breeding with fitness. If we define this really carefully, breeding with fitness is going to turn out to be Gibbs sampling in a Markov random field. So you'll have that twice in one day. Let's do this. So, breeding with fitness. First of all, sensor 1. Select k randomly, kill theta k, repeat. Propose theta k tilde new theta k, distributed to, I don't know, mutation with probability U, new mutant, probability 1 minus U, uniform. Okay. With probability F of theta tilde K, accept. Until accepted. This is one valid breeding rule. This is one valid breeding rule. Well, there are others which I'll go to, but I've defined this with some care, okay, so that we have a Gibbs sampling proposal, and then we accept. Then these F's work by rejection sampling. Okay. Now, I claim. Shall I rub out this one? Yeah, let's do this one. Getting up to closing time, but let's get there. God, this is extraordinarily well timed. So, claim. Okay, yeah.
What does W dot P mean?
Oh, with probability. This is with probability means with probability. Can't write. My fingers are covered in ink. With probability. So this is just like tiny genetic algorithm breeding, except once I've killed, I shoot bull K in the urn. We've got to replace it. Bull K's gone. So we carry on proposing until we accept one. Okay. Now I claim with this breeding system that P of equilibrium at equilibrium P of theta minus n equals, if you like, the beta binomial equals, shall I call it Polylearn distribution, beta binomial? Let's call it beta binomial equals beta binomial of theta 1, theta n, given alpha 0, alpha 1, okay, times f of theta 1 times, right, so it all factorizes. Now this is the big payoff, this is the payoff. So this term here, this is the prior, this is TGA with no selection, no, sorry, proportional to, with no selection, that's going to be, okay, so this is product of all fitnesses. So I think I may now I think I'll come revisit this next time and go over proving this next time. What I'm going to do is sort of just make an intuitive remark about this here. What I want to say now is where we've got to, because I sense people may require a little motivation. Okay? You might just need a little motivation. I haven't said anything at all about f. F is an arbitrary function of thetas. Oh, you said, hang on, these thetas aren't terribly interesting. They're only zeros or ones. Oops, I forgot about that. So I could, if it's a function of 0 or 1, it's only got two values for it, so it's 0 and f1. Oops. The reason this is cool is because we've got an explicit representation of the equilibrium distribution. That's wonderful. This is great. This means that we can do all sorts of things. We can try and find out what it is, that we can use other Monte Carlo methods. Oh, wow, this is only for a tiny genetic algorithm. So I'll just prove this next time. It's not hard. You can sort of see it. What about, shall we have an interesting genetic algorithm, IGA, or just GA? Interesting genetic algorithm. Interesting genetic algorithm. We've got, I don't know, we've got theta 1, 1, to theta 1, n, theta 1, 2, to theta 2, n. Sorry, I can't put n1, can I? And this is an interesting GA. By interesting GA, I mean L tiny GAs all next to each other. As we will see next time, we can make the tiny GA considerably more interesting than it is with just 0 or 1. We can have arbitrary objects in it, not zeros or ones, and use the Dirichlet process and make it very interesting indeed. Indeed, the tiny GA, as I described it, with an arbitrary distribution, the mutations from an arbitrary distribution, not just zeros or ones, is also known as, with selection, is also known as the Dirichlet process mixture model, which is a pretty hot object of study in machine learning right now. So what I'm doing is we're putting lots of these together, and then we have the f here. We have f of theta 1, comma. We have our fitnesses here. So we take the fitness of the whole lot here, and the f1 equals fn equals f of theta n1 theta nl. So we describe, so as in normal genetic algorithms, we have fitnesses of a whole genome. So this thing here is one genome. But let's think of this as a whole table of random variables. Each column is a tiny GA. Each row is a genome. Now, if we breed by shooting an entire genome, erase the whole genome, then we repeatedly propose along here, just from these columns, and then accept according to fitness, exactly analogously to this. What we've got is a Markov random field with column probabilities, which are given by priors, and row probabilities given by fitnesses. And the probability of the whole thing factorizes into the product of column probabilities times row probabilities. Now that's cool. What this means? Well, what can we do? Damn, well, we ought to be able to do some theory. Okay, that's quite cool. Actually, we've got an explicit representation of the mutation selection distribution of this thing. Hey, that's nice. It means that we could define other Markov chain Monte Carlo methods, not this stupid Gibbs sampling, also known as breeding, which provably converge to the same distribution. We can do it column by column. We can say, hey guys, this generation, the population is going to get together, and we're going to just concentrate on column 23, and we're going to breed with that. And you've got to, genetic algorithms are sold as optimization methods, right? They're supposed to be optimization. Well, this isn't optimization. This is like Bayesian inference. These fitnesses are kind of like likelihoods. These columns are like priors. So, yeah, okay, we can try to optimize if we allow the prior to go to, so that it's either all ones or all zeros in each column. But this could be doing something much more interesting. It's converging to something which is not the fitness optimum. It's converging to something which is, if you like, the joint probabilities distribution. We've got a priors in there as well. Damn, what are those doing? Oh, finally, let's just think about nature. Remember the absolute paradox that I tried to convey to you in the first lecture. I'm sure you can't, because it was ages ago. And whatever. The wildest thing, which is utterly amazing when you start thinking about it, is that what we egocentrically think of as being like the most sophisticated organisms in the world, us, dolphins and elephants, happen to live in the smallest numbers and the slowest reproduction rates. How do we compete against malaria parasites, which exist in zillions and reproduce like crazy sexually? It's pretty wild. How do we compete even against flies? What about protozoans? Protozoans are sexual. And why aren't the protozoans evolving like crazy and eating us all? Well, I mean, they do occasionally, but not that often. The key point, this is actually a sexual model. Notice this is a slightly weird sexual model. I'll go into that next time, in that we get kind of crossover. Actually, we get kind of n-way crossover. Because whenever we breed something, we're taking something out of lots of different genomes. But this is kind of morally equivalent to crossover. Now, with a sexual population, let's just think about mice. Let's think about mice as a sexual population. All these little mice. And you get mice everywhere. You get mice in England. You get mice in London. My sister has mice in her farm on Wales. Wales, it is permanently raining, with rain coming in kind of like omnidirectional rain. And they have to kind of run around outside and have holes that exist in holes in soggy wet fields. But it's the same species of mouse that is happily infesting this building. Pretty adaptable little creatures, but it's the same species of mouse. They can interbreed as gene flow between mice here and mice that are sort of happily living in the south of France. They're very widely distributed. All these mice have different fitness functions, but genes flow pretty readily between the populations. We'll talk about gene flow later. So wait a moment. Here, I want to put up something which is rather neat. I want to have a distinction. We can have different fitness functions. We can have F1, F2, and Fn. There's no, let's call each of these things a niche. So all of these things can have different fitness functions. And then, what sexual evolution is doing is it's producing a compromise solution which has a compromise between the prior distribution, which depends on the mutation rate of that, and a whole range of different fitness functions. And we can even subdivide this into different populations if we want to. But let's not go there. So that's where I'm going. But the cool thing about this approach is that I've very carefully defined breeding is in a shoot one first and then breed replacement. And very carefully defined breeding with fitnesses, so that the whole process of breeding, it's pretty much as implausible as ordinary genetic algorithm models, but it's exactly interpretable as Gibbs sampling in a Markov random field, which means we can do lots of other things and relate it to lots of other theory. So that's where we've got to now. I will recap and review some of this, and if any of you, I'll prove this claim next time, which will involve a certain amount of recap. Some of you may want some recap, and if anybody with particularly good handwriting wishes to give me notes, I will translate this into. Of course, you may wish to keep them all to yourself.
My handwriting is appalling.
Sorry?
My handwriting is appalling.
Handwriting is appalling. Or alternatively, I'll try and do it from memory. It's kind of useful because as I'm talking to you, I'm gazing at you not merely to check whether you are awake, but also to check what I need to explain. And so writing it all out beforehand is hard because I don't know what you're supposed to know and what you're not.
If you want to try, you can use mine.
Thank you very much.
That's okay.
Okay. Do you want to photocopy me first, or?
It's okay. I trust you.
Just, okay. Sorry. And what's your name? I will write your name on the chat.
That's a good idea. Yeah, it's Mike Seville. Mike Seville.
How do I spell Seville?
S-E-V-I-V-L-E.
Seville. Right.